Thanks, guys. So my name is Sean. I'm a developer and a support engineer for GameSparks. Some of you might have heard about GameSparks. We're a back-end as a service platform. I'm going to talk a little bit about that later, but I'm a tech guy, so this is sort of a light tech talk, sort of a retrospective of a feature that we added last year for real-time multiplayer networking. It came about by a collaboration with Hutch Games, who were one of our customers at the time, and it's sort of just a journey on the decisions that we made and why we made them and what problems there are with developing real-time multiplayer networks for mobile games. So I'm a tech guy, but the sales and marketing people for GameSparks would be really annoyed at me if I didn't do a little bit of a sales pitch. So to explain to you very briefly what GameSparks is about, we do sort of anything that you can think that would go onto the cloud part of your game services, we cover that. So these would be things like social authentication and social integration. So for authentication, it would be Google Play, Apple, Twitter, Facebook, that kind of thing. But we'll also do third-party integrations for payments like the App Store and the Play Store, and also things like Amazon. This would also include in-app purchases and receipt validation and virtual goods. So the social is a core part of the platform. So we also do things that you'd expect from a social game services like leaderboards, chats, achievements, and push notifications. We have a big suite of analytics. At the moment, the analytics is kind of like a Google Analytics thing. So it's key events, DAU, retention, ARPDAU, that kind of thing. But we are unveiling a new, more flexible suite of analytics tools, which is based on feedback we've had from our customers to basically do whatever weird analytics needs they have, and reporting and exporting. So on the developer side of things, we have a couple of cool features like cloud data and downloadable content on the blob. We also have this concept of cloud code, which allows you to create custom events. That's some JavaScript. It allows you to create custom requests that come from the client to the server. You send whatever data you want, you customize it however you want, and then you run some JavaScript. And that JavaScript could be reading and writing to the DB, just running some maths on whatever you need, or patching out to another web service to get something, and then forming the request and sending it back to the client. So what I'm talking about today is the multiplayer aspect that we have. So the company's been running for about 4 years now. We've about 170 million players, 10,000 registered developers, 600 live games, 7,000 games in development, and at our max last year, so our big sort of server capacity thing that happened last year is one of our games hit over 500,000 concurrent users at one time, and that was in the space of about 2 or 3 days after launch. So we have games published by some big studios, like big studios and publishers like Telltale, Bandai Namco, Square Enix, Rovio, Amazon Game Studios, Capcom, and Ubisoft, and we have a bunch of other games on there as well. So how the real-time services started off was Hutch Games had already made a game with us in 2015 called MMX Racing. And they used basically the core part of our services, which is virtual goods, leaderboards, and social integrations. That's what most of our customers use from GameSparks, or they mix and match parts of that. They approached us, asked us to develop a real-time multiplayer network. They weren't the first to approach us, but we had a good working relationship with MMX, and it was a good opportunity for us to not just develop these services and then release them and hope that they worked. We were able to get a company that we knew we could trust to work with, that were happy to work with us, to develop these services to their needs and iterate it through it so that we can develop it, test it with this game, and then say, now we have a great system, let's release it to the rest of our customers. So what the next part of this talk is about is just sort of what challenges there are for developing real-time multiplayer network services for mobile games. So the example that Hutch needed was really simple. It's a head-to-head racing game, and they really only needed 3 things to be sent, which is the position of the players on the track, the speed of each player, and the drift angle. And then they needed the ability to intercept packets to provide cheat detection, and that was pretty much all they needed. The biggest problem with developing real-time networks for mobile games is the fact that there are huge bandwidth limitations. You don't have the same speed that you have with a broadband network, and the coverage is very unreliable. That's a 3G coverage map for, I think, Vodafone, and it looks like this is a pretty extensive amount of coverage, right? But the problem is that the mobile providers do not provide you with, when they say they provide you with 3G, that only means that they're providing with 3G when they want to. So there's no limitations for them to decide, we need more bandwidth somewhere else, and now you have 2G. The other problem is that mobile games are played when people are traveling. And you're never guaranteed that you're traveling in a 3G network area for the duration of your journey. That causes huge problems that are not the same as networks that are used for multiplayer games on consoles or PC. If you have a crap connection when you start off, you're going to have a crap connection halfway through your game. That's not the same for mobile. So the biggest problem is the latency issues caused by these unreliable networks. And this is not something that GameSparks can solve. So what we focused on was, what do we have control over, and how can we get the fastest network possible? So I don't want to get too much into the sort of technical background of network design, but something that's always interesting when you're talking about making a network and making those decisions is what transport protocols do you use? Do you use TCP or UDP? And these are, so basically TCP is the internet paradigm for how you send packets, how you send data across the network. And how TCP works is the sender computer sends a message to the recipient saying, I want to send this data, this is the amount of data, and this is the order it's going to come in at. And then the recipient computer sends a message back to the sender saying, okay, send me the data. So this is really good because all of the packets, all of the messages are sequenced, so they arrive, even if they arrive out of order, they can be rejoined in the right order, and the recipient computer is happy. Because the recipient knows what you're sending, it can correct for errors, or if packets are lost in the network, because it has to send them over the internet, and the internet is not always reliable. If a packet is lost and the recipient computer is waiting for it and it never comes, it can send a message back to the sender and say, I think you were supposed to send me this, please send it back. So in contrast to UDP, UDP doesn't have any of this. So UDP is effectively, I want to send this message to this IP address and this port, go. And then it doesn't care if you get it. So the obvious thing for most people, if they would encounter these networking paradigms, is you use TCP, because why would you ever use UDP? And the actuality is that nobody really uses TCP for game networks. A big reason for this is because of the extra stuff that TCP has when you're transmitting the data. It's just bigger. The packets that you're sending are bigger. So UDP is a lot smaller. It's usually about 60% smaller. TCP also does not give you full control over when you send it, whereas when you want to send a UDP packet, it's sent. Depends on your router and stuff, but it generally is sent. So most networks use UDP. The problem with UDP is that Hutch needed a network for a racing game. And because UDP is not sequenced, there will be this problem if we develop a network just with UDP, which is you send the packet now, and the packet that you send now gets a little bit delayed, and the new packet arrives out of order, and all of a sudden you're getting a position update from a position that's old. And that's a very bad thing to design if you're making a racing game. So our solution was pretty simple. It was just to make an ordered UDP protocol, which is the advantages of having TCP. So, well, some of it, if a packet arrives out of order, if it's too old or too late, it's dropped. You ignore it. But we have the flexibility of having a much lighter packet, and it's less data, and the less data means more speed. Because we're availing this to all of our other customers, we just decided to put all of it in. So you want to send a packet, we don't care how you send it. We give you the option of UDP, TCP, or ordered UDP. So the next thing to consider is the network distribution, and this is also huge because Hutch had many million players on, I can't remember how many million players, but many million players on MMX Racing, and we can expect the same for whatever game they're going to make. it's going to be a global network. So how do we deal with having game servers, let's say, situated in Europe, players in the US and the UK, and now we have to send packets in that network, and it's obviously going to take a hell of a lot longer for the packets to go from the US player to the server than the UK player. And the big problem with that is, even though the UK player is closer, it degrades the gameplay experience for both players. So both players have to be in sync in order for the game to run properly, but they can't be in sync because there's so much lag from the US player that it's going to degrade the gameplay experience. There are ways around this, but it's easier just to basically build a distributed network. So what we did is we changed the way our matchmaking worked to start these games. So instead of entering a match based on one level, which would be like your skill or your level or something like that, you enter your match. When we're doing real-time matches, we always check the region you're in first. And then we find a server that we can distribute, so we can set up clusters, real-time clusters, wherever we need them. And when a new game starts, we can spin up a new instance of that game and have all of the people from that region match that server. So I'm not going to talk too much about peer-to-peer, but the next thing we have to consider is, are we going to use peer-to-peer networking or server authoritative networking? For peer-to-peer networking, you're sending packets from one player to another player, and those players are sending them back. This usually means that one player has to be authoritative, which is that one player has to kind of keep a track of the state of the game. This has a bunch of problems, like what if that player gets disconnected? You have to do some very complicated stuff to get the next server to take up the mantle of being the host and transfer all that data. You also have huge problems with the bandwidth. The more players you get on a peer-to-peer network, the more bandwidth you take up. There is another disadvantage, one advantage over peer-to-peer with comparing it to server authoritative models, is that if you have two people sitting on the train playing it right beside each other and it's peer-to-peer, they don't have a very long distance to go. Whereas if you have a server in the middle, the players' packets have to go from the first player to the server and then to the second player and then back. So there is disadvantages and advantages to peer-to-peer. But in our case, server authoritative is a lot better. The main reason it's better is because one of Hutch's requirements was that they needed to be able to intercept packets to check for cheating. If we have a server running all of the network, then we can do that. So the server basically, you send a packet, player 1 wants to send a packet to player 2, they send it to the server decides is it a valid packet, and then it sends it on. The disadvantages, of course, are what I just said, but also because you've got to maintain the server. And you've got to scale the server, and you've got to run up instances of your game as they're needed. But GameSparks already deals with this all the time. So GameSparks is it's a backend as a service platform. So we have DevOps people who deal with this all the time. So by having this distributed network and the server authoritative model, we don't need to have, we have local clusters, and then when we want to spin up an instance of the game, we can do that on the fly and have it scale whatever way we want. So yeah, these are the advantages: the load balancing, being able to scale vertically or horizontally as we need them, and we have control over it. We can add our own network monitoring tools, and we can build a distributed network. But what we can also do, because GameSparks, the GameSparks portal, which is your way of managing all your GameSparks features, it has its own IDE in it, the JavaScript IDE that runs the cloud code. So what we're also able to do is to set up hooks that allow packets that come in from the client to be associated with callbacks in your cloud code. And now you can have a server authoritative game. So your server can literally run the entire game. All of the data and the game state stuff can go on the server rather than having to have one client run it. What we can also do, because the real-time clusters and the GameSparks game clusters are different, but because we've built both of those parts, we can add hooks in our real-time scripts that allow you to communicate from your real-time game to your database, to your social authentications, use your push notifications, use your leaderboard features, and do whatever you want. Okay, so that's basically the model of our server. The restrictions are always going to be latency. So what we thought about at that stage was what else do we need? And if you look at other multiplayer networks providers, like let's say, for example, Photon or Unet, usually they're going to have clock syncing. Clock syncing is, other than making a server, making a network that works, clock syncing is probably the most important thing for games. You need to make sure that if you have your server and you have a latency of 30 milliseconds to player 1 and a latency of 100 milliseconds to player 2, they have to be getting the game updates at the same time. There are sort of game design decisions that you can use to overcome these lags, but if you have a good clock sync or if you have good sync on your network, the server can take care of that and it can delay packets, and you can get your game designers to kind of fill in that delay with different kind of game design techniques. The second thing is predictive movement. If you want to have your server authoritative of all the movement and all of the players in your game, predictive movement is incredibly important, and it's also a basic part of having like a complete server authoritative architecture. You don't want clients to say, the players say, I'm moving here, and the server decides, the server pretty much says, well, I'll be the judge of that. And then it decides what position updates to send to everyone else. The other thing that's really important for people is network analytics, like your latency, your bandwidth analytics, packet analytics, and what kind of reports and charts you need for that. So what we decided on was we had a network that was as lightweight as possible, was incredibly flexible with network distribution, allowed you to hook into our cloud code and gave you an IDE that allowed you to run a bunch of other stuff, basically whatever you wanted. And if we put all this other stuff in, we'd be taking up bandwidth and limiting developers' options. We'd be introducing things into the network that developers didn't necessarily need and then eating up all of their bandwidth. So what we decided on was sort of, it sounds like we just didn't want to do the work. But what we decided on is not to do that. We just basically allowed them to do whatever they wanted with the scripting engine, hook into the database and whatever other functions they want, and the tools are there and the tutorials and docs are there for them to build out the server the way they want. So if you want to send a packet for GameSparks, there's pretty much just one int and then whatever else you want. This is all optional. There's an opcode, which is your tag for what this packet does when it hits the server. You can choose your delivery intent, which is unreliable UDP, unreliable sequenced, or reliable TCP. And then we have this RT data, which is a JSON wrapper. So you can put incredibly complicated data sets in there. And then you just pretty much pick your recipients, and if you leave this out, it goes to the server only. If you put a number in here, it's it's a player 1, player 2, player 3. So this is how we kept the network as fast as possible. And we allowed the developers who wanted to use this network to do it themselves. We didn't want to mess with them. We didn't want to get into arguments saying you're using the wrong type of clock syncing or you're using an inadequate prediction model for your predictive movement. So I was going to talk about Hutch's new game, but they're going through some rebranding at the moment. So another company that adopted our real-time services very early on was Fun Punch Games, and their game Striker's Edge. It's releasing in 2017. It's a multiplayer action game for Steam and PS4, and we worked with them at the start because they were quite early adopters of the RT stuff. But interestingly enough, they used our real-time services, but they built their own matchmaking services. And we do offer extensive matchmaking services. And instead, they didn't use any of our leaderboards. They used our databases, and they used some of our social authentication. But other than that, they sort of adopted the parts that they wanted. So that's sort of the main takeaway from the talk was how we minimized what we needed to build and brought it down to the bare essentials to give developers what they needed without restricting them or taking bandwidth away from them for reasons that they didn't need, and allowing them to just use GameSparks in whatever way they want and pick and choose how they're going to work. So that's it. I don't think it'd be an insult if I asked for questions at this stage, but
we've got time for one question.
Yeah.
Anyone's got a question?
I'll be upstairs anyway. So.
Can you tell a bit about packets over TCP? Because sorry, can you tell something about packets over TCP? Because
you know, we are developing a game and we're using Darkrift and we are like losing packets, and it seems like you shouldn't be you shouldn't worry about this because TCP should know that the packets are lost. But
so we're getting kind of cut in for time. So I'm upstairs on the second floor. Do you want to just come up and talk to me afterwards?
yeah, okay.
Cool. All right, we'll leave it there.
Thanks, guys.